The last speaker of this session for Prof is Alon. He's going to talk about the dark opera.
Thank you very much for the organizers for this wonderful workshop. And what I'll talk about today is about work that originated from a formalism for quantum mechanics, which I developed with Marco Mattone between 96 and 2000. And in September last year, following the opera claims, Marco wrote a paper where he proposed that our approach leads to superluminal neutrinos. And since I did not think that I should, if there is fame and glory to be found, I didn't think that I should leave it to Marco to get all the credit. So I wrote a counter paper where I stated that our approach does not necessarily lead to superluminal neutrinos. So this is this paper, and then I wrote a subsequent paper where I proposed that our approach can attribute to the dark energy. So, so the motivation for pursuing this work is the disparity between general relativity and quantum mechanics. General relativity arises from a principle of covariance and the equivalence principle. So there is a fundamental geometrical principle underlying general relativity, while in quantum mechanics there's no such principle. There is axiomatic formulation based on the probability interpretation of the wave function, but the scheme or the framework to combine quantum mechanics with gravity is at present not known. The main effort in this regard is the quantization of general relativity, e.g. quanta is quantization of space-time, for example in the context of string theory. And the main successes of string theory in my mind is that it provides a viable perturbative approach to quantum mechanics, to quantum gravity, while at the same time it gives rise to the unification of gravity, gauge, and matter structures that we observe in nature, and therefore it makes possible the constructions of phenomenologically realistic models, and is therefore relevant for experimental observations. And the state of the art in this context has been the construction of minimal supersymmetric standard models from string theory, and the first was constructed back in this should be 89 rather than 99, and with Jerry Cleaver, who is here in the audience. So the model itself was constructed in 89, and with Jerry Cleaver we analyzed flat directions in this model and demonstrate that indeed it leads to the minimal, the spectrum of the minimal supersymmetric standard model. And since then there's been a lot of work in this direction, which part of it has been reported in this conference. So our approach to formulating to quantum mechanics has been from adaptation of the Hamilton-Jacobi formalism of classical mechanics. So if you recall Hamilton's equation of motion, then what the Hamilton-Jacobi formalism in classical mechanics entails is that you make a transformation from your initial Hamiltonian to another Hamiltonian in which the new Hamiltonian is identically zero, and therefore the Hamilton equation of motion vanish for this Hamiltonian. So the phase space variables in this for new Hamiltonian are then constants of the motion. And the solution to the classical Hamilton-Jacobi formalism is, or the solution to this setting this problem, is the classical Hamilton-Jacobi equation. And in the stationary case it takes this form. Now the important point here is that the transformations from the old set of variables to the new set of variables is via canonical transformations, which treat the phase space variables as independent. So you treat them as independent. When you apply the transformation, you then solve the Hamilton-Jacobi equation, you integrate the Hamilton-Jacobi equation, and then you extract the functional relationship between the phase space variable. Now we know that quantum mechanics tells us that the phase space variables are not independent, and therefore what we aim to do in our approach is to formulate a similar question. So you find a transformation, say, from your starting Hamiltonian to another Hamiltonian, in which you impose that this function in the classical, in the Hamilton-Jacobi equation is 0, and then but you don't assume that the phase space variables are independent. You assume that there is a functional relationship between them when you apply the transformation. So the equivalence postulate states that there's always a transformation, a coordinate transformation, and there is a generating function and the functional relationship between the phase space variable, and there is a transformation to a new set given in this form. So it's just a coordinate transformation, such that it's always possible to find a state where this function vanishes. Okay, where your kinetic and potential energies are trivial. So we insist that this exists for all possible functions. And what it leads to the fact that you need to deform the classical Hamilton-Jacobi equation, and it leads to a quantum Hamilton-Jacobi equation, to the Schrödinger equation. So let's see how this comes out. So the principle or the postulate implies covariance of the Hamilton-Jacobi equation. So I mean, and you see that this equation is not covariant under the coordinate change. In particular, the state where this function vanishes is a fixed point under the transformation. So you cannot connect all possible states by the coordinate transformation. So what this implies that you need to modify the classical Hamilton-Jacobi equation by some, for example, by adding an additive function. This equation should transform essentially as a quadratic differential. So the two terms should transform as a quadratic differential. So this imposes that this part of the equation transforms as a quadratic differential plus an additive term, and the second part transforms as a quadratic differential minus the same additive term. And then this entire equation will transform as a quadratic differential under the transformation, where the generating function transforms as a scalar function under the transformation. So there is, for some reason, a figure that is missing here, but basically what we consider is a transformation between three states, so QA, QB, and QC. So you go from QA to QB, and then from QB to QC, or you go directly from QA to QC. Now, with this hypothesis, first of all possible states arise, so all possible non-trivial or states characterized by this non-trivial function WQ arise from the inhomogeneous term that arise from the states for which this term is 0, according to this transformation law. So if you consider these three states, you get a cost-cycle condition. So this is the cost-cycle condition that you get by these transformation rules. And what you can show that this cost-cycle condition is invariant. So you can prove a theorem that this cost-cycle condition is invariant under model transformation of the cost-cycle condition. Now, in one dimension, this Mobius symmetry uniquely fixes the cost-cycle term, or this inhomogeneous term, to be given by the Schwarzian derivative, and the Schwarzian derivative transforms as a quadratic differential up to an inhomogeneous term, and it has a property that it is invariant under Mobius transformations. So now you can form, there is an identity that you can form from Schwarzian derivatives. So this is a quadratic differential on this side, and this difference between two Schwarzian derivatives transform as a quadratic differential. This is an identity, so you can check that it's indeed satisfied. Now, if you make the following identification, so you identify WQ with the first function and the quantum term with the second function, then the modified Hamilton-Jacobi equation takes this form, and in the limit that beta goes to 0, you get back the classical stationary Hamilton-Jacobi equation, so your solution becomes back the classical solution. Now, from the properties of the Schwarzian derivative, and from the fact that we set this function to be given to this Schwarzian derivative, from the properties of the Schwarzian derivative, this function is a potential function in a second-order differential equation, which is given in this form, and the argument in the Schwarzian derivative is given by the ratio of the solutions of the two functions of this second-order differential equation. So this is you can use this second-order differential equation, which is essentially the Schrödinger equation, in order to solve the nonlinear quantum Hamilton-Jacobi equation. So this implies that beta, the coefficient or the parameter that we identified here, the covariantizing parameter, is essentially h bar. The general solution to this equation is given in general by this function. So the two solutions of this second order differential equation. And an important property of our formalism versus, say, the ordinary approach to say, Bohemian mechanics, or even or the ordinary formalism of quantum mechanics, is that our formalism dictates, since this function is given by the ratio of these two solutions, our formalism dictates that we must use the two solutions of the Schrödinger equation. This is reminiscent of what you have in relativistic quantum mechanics or quantum field theories, in which it is imposed that both solutions, say, of the Planck-Gordon equation or the Dirac equation, are necessarily have a physical implication. This is something similar that arises here. You can use this the solution of this equation to solve the nonlinear quantum Hamilton-Jacobi equation, and the solution is given in this form, where this quantity W is the ratio of the two solutions of the second order differential equation, and this is a complex constant, and L1 is necessarily non-zero, and alpha is real. Now, this generalizes to any number of dimensions. The cross-cycle condition is generalizes to d-dimensional with respect to the Euclidean or Minkowski metrics, and it is invariant under d-dimensional Mobius or conformal transformations. The quadratic identity that was found in the one-dimensional case also generalizes to higher dimensions and takes this form in Euclidean space. So this is again just an identity where you identify the first part with the classical potential function, and this part with the quantum potential. So this is in Euclidean dimension. This is in Minkowski space-time, and this is in Minkowski space-time with some gauge interaction. So the structure generalizes to any number of dimensions by this underlying mathematical structure. Now, so in the relativistic 1 + 1 dimension case, you start with a Klein-Gordon equation. You can insert the wave function in this form. So this is an either, another typo, and you get a relativistic quantum Hamilton-Jacobi equation with this continuity equation for the R and S naught. And the quantum potential takes this form with the momentum given by the gradient of S naught. So you get the energy relation in this form. So this is a quantum deformation of the classical energy momentum relation, the classical relativistic energy momentum relation. In 1+1 dimension, you can solve the continuity equation for R. So you get it in this form, and the quantum potential then takes is written in terms of the Schwarzschild derivative. So you can write this equation in this case in this form, and then it takes the form that it took in one dimension, and we can again solve it using the method that we solved before. So this is just given in terms of this Schwarzschild derivative. So we can use the second order or the solution of the Klein-Gordon equation to solve this nonlinear quantum Hamilton-Jacobi equation, where this W is given as a ratio of the two solutions of the Klein-Gordon equation. Now we can use the Jacobi theorem to define time, and so time is given in this form by the derivative of S naught with respect to E. We can write it in this form, and then we obtain this relation, from which we can take the derivative of time with respect to Q, and we therefore get this relation, which you can invert and get the instantaneous velocity. So you get this relation for the instantaneous velocity, and approximating this term here as being small, so much smaller than 1, you get this modified dispersion relations for this is just a classical piece, and you have the modified dispersion relations for the relativistic velocity or relativistic speed. So Marco used a slightly different setting to argue that this term is always larger than 1, but I think that you can see that the dependence is quite complicated. So for the solutions of the Klein-Gordon equation, the dependence on the parameters is quite complicated, and you can check it numerically for various cases, and you can see that indeed you get modified dispersion relations, but not necessarily superluminal. So this was the argument of the first paper. Now you can regard so now I will shift to the second argument. So using the properties of the Schwarzschild derivative, we can change the variables from S naught of Q to Q of S naught, and you can use this then the Schwarzschild derivative has this relation. So again, this is a mathematical identity. So we can rewrite if you recall how the quantum this was the form of the quantum Hamilton-Jacobi equation. So we can rewrite it in the following form. We can absorb the quantum term into the kinetic term here by redefining our coordinates in this form. So this is just a classical form, and we see that what the quantum potential in this form just affects the geometry of the space-time. Flanders showed back in 1970, showed that the Schwarzschild derivative can be regarded as a curvature term, and in higher dimensions, indeed, the quantum potential is related to the curvature of this function. So you can argue that in this formalism, the quantum potential is an intrinsic curvature of the particle. Now you can show, or you can argue that the formalism indicates an intrinsic length scale, and the reason is that for the state for which this function vanishes, the second order differential equation takes this form, and it has the one solution with just q naught, and the second solution which is a constant with a length with a dimension of length. So the formalism intrinsically implies, since we must retain the two solutions of the second order differential equation, it entails an intrinsic length scale in the formalism. You can you can then solve find the solution for the quantum Hamilton-Jacobi equation in this form, and the momentum will then be given by the derivative of S naught with respect to Q naught. So it takes this form. Now, so here this constant L naught acts as an ultraviolet cutoff, since it is necessarily non-zero. This is an implication of this equivalence postulate. And if you take the classical limit in which h bar goes to 0, and keeping or requiring that p naught goes to 0 in this limit, implies that this constant, which has a dimension of length, the fundamental constant with dimension of length that satisfies this requirement that p naught goes to 0 in the limit that h bar goes to 0 is given by the Planck length. So the Planck length is a choice which is consistent with the classical limit. So we can set L naught to be given by the Planck length, and then we can extract the quantum potential, which takes this form. We can perform some numerical estimates. So Q naught is given by the ratio of the two solutions of the second order differential equation, and consistency of, since the trivializing transformation is given by the ratio of these two functions, consistency of the formalism indicates that this function, this ratio of these two solutions, has to be continuous on the extended real line. So it has to be continuous on the real line plus a point at infinity, and this is a condition which is reminiscent of this is a condition that leads to quantization in this formalism, and it is reminiscent of the way that quantization arises when you are in a compact space. So this condition essentially implies that if you wish, that the universe should be in fact compact, and we can therefore, taking this as an assumption, we can make some numerical estimates of the size of this quantum potential. So taking, say, m to be of the order of 100 GeV, and this to be given by the Planck length, and the Q naught to be given by the size of the observer universe, we get that the size of the quantum potential is of the order of minus 10 to the minus 202 electron volts. So it's very, very tiny. Now it's still a relevant question: what is the effective scales that we should take for Q naught? If you take it 1 meter, you get something like 10 to the minus 96 electron volts. So it's still quite small. So it's still, this I think is a relevant question. What is the effective Q naught? But we see that this is an intrinsic energy of the elementary particle, which is never vanishing according to this equivalence postulate, and is similar to the rest mass of the elementary particle. Now this formalism generalizes to the multi-particle case, so you can write, say, the Hamilton-Jacobi equation for the two-state case with R1 and R2. So it will take this form. You can set R equals to the relative position, and RCM equals to the position of the center of mass, and then you can write the equation in terms of the center of mass motion and the relative motion, and then the center of mass motion takes this form, and the important point to note here is that m is cumulative, so essentially the dark energy and the mass will add up. Okay, so this brings me to my conclusion. The equivalence postulate implies that S naught, first of all, it implies that H bar is non-zero. It arises as a covariatizing parameter in our formalism, so it tells you why quantum mechanics is necessary. And S naught is never a constant. This implies that the two solutions of the Schrödinger equation must be used for consistency, and real L naught can be identified with the Planck length. So there is a fundamental length scaling of the formalism, which somehow also implies that gravity is somehow intrinsically in the picture, or in the formalism, embedded in the formalism. The quantum potential takes this form. The minus is wrong here, but takes this form in the one-dimensional case and this form in the multi-dimensional case, and it is an intrinsic curvature of the elementary particles. The fact that S naught cannot be a linear function of the coordinate, so it cannot be a slightly stronger constraint than that, is that it's not related to phase-space duality. It is not cannot be a linear function of the coordinate, leads to the condition that this quantum potential is never vanishing. So it's an intrinsic energy of elementary particles which is never vanishing. As an outlook, this equivalence postulate is tightly connected to phase-space duality, which is an aspect that was developed in parallel. And this phase-space duality, you can regard it as, you can regard T-duality as phase-space duality in compact space. So you have, I think this is one possible link with string theory. And you can view this approach as an axiomatic approach to quantum gravity. Namely, you pose the postulate, and everything else follows from the mathematics. And at the end, if one possible sort of long distance goal, or maybe not so long distance, is to try to see how essentially the symmetries that underlie the formalism overlap with symmetries that we know to exist in string theory, primarily the conformal symmetries, and then try to see what is the relation, to use this approach to, in fact, to derive string theory. Well, thank you.
Very interesting. Do you have a question? Apart from coming for coffee. Okay, if there's no questions, thank you very much, Alan.